Hey there everybody, welcome to today's Cosmology segment. This one's completely separate from our daily space weather videos. First thing we're going to look at is cosmic rays. So here is the Apatity neutron monitor. You can see the 24-hour chart and the 30-day chart. We're actually seeing an uptick here at Apatity over the past 30 days. Tiny little uptick there. Barentsburg, a small uptick at Barentsburg as well. Let's go a little farther south to Athens, Greece. And here's the Athens, Greece chart. 30 days worth of cosmic ray data from the Athens neutron monitor. And over 30 days there at Athens, it is looking flat. Let's go even farther south to Mexico City. Here's a Mexico City cosmic ray monitor, and we're seeing a bit of a downtick there at Mexico City. And let's go back up north to Oulu, Finland. There's the Oulu chart. Flat over the past 30 days. It's this middle pane. And we'll take a brief look at DOMC Antarctica and DOMB. There's DOMC. Flat over the past 30 days at DOMC. DOMB. Similarly flat over the past 30 days. And just so you know, cosmic rays may be more important than you think. They are associated with climate and weather and, well, other things that we won't tell you about in this cosmology segment. We just wanted to update you on the current state of affairs with cosmic rays. Next, let's talk about metal-poor stars. Metal-poor stars. And this particular This particular metal-poor star, known as S plus J 2104-0049, is the most carbon-poor star ever discovered. So you can find this article here on phys.org in the Astronomy and Space section. And when we're talking about metallicity in astronomy, folks, metallicity is the abundance of elements that are more massive than helium on the periodic chart. So the periodic table of elements, everything from lithium on down, is considered metal, and metal-poor stars are important as they perhaps give us insight into things like stellar evolution. So perhaps check out this article on the most carbon-poor star ever discovered, S plus J 2104-28.01-004934.2. The lowest carbon abundance among metal-poor stars so far detected. This discovery opens the possibility of finding additional ultra-metal-poor stars directly from narrowband photometric surveys, a potentially powerful method to help complete the inventory of such peculiar objects in our galaxy. How does stellar evolution really work? Well, we're hoping the channel will help to advance these facts. How about a new space instrument capturing its first solar eruption? Oh yeah. So we spend a lot of time watching the sun. So does the solar orbiter. It's caught its first coronal mass ejection back in February. And here's some imagery from that. It's a coronal mass ejection as viewed from the solar orbiter. So the ESA spacecraft there. That's the Solar Orbiter Heliospheric Imager, known as the SoloHigh. Getting a sudden gust of wind, solar wind that is, from that coronal mass ejection. So here's what it looked like from the perspective of stereo A, and once again we spend lots of time looking at stereo A on the channel. Here's the coronal mass ejection from stereo A's perspective, and again here it is from solar orbiter's perspective. Just a fantastic view there, and quite high resolution. You can see these, they look like shell layers pulsing out there. And you can see the background stars moving across as well, due to the contrast required to take images of plasma. So here's another view. This is the ISWA model. So another article here from phys.org about the solar orbiter taking its first coronal mass ejection imagery. And the next thing we'll do is we'll zoom way in to the Cygnus Nebula. Yes. So you're currently looking at infrared light. This is the Cygnus Nebula. We're going to zoom into one of the most important objects in the Milky Way galaxy, at least from the perspective of our solar system and planet. It's Cygnus X-3. And what's so interesting about Cygnus X-3? Well, I don't want to go super in depth into it, but Cygnus X-3 is a high-mass X-ray binary consisting of a massive object, a massive radio source orbiting a Wolf-Rayet star. This is the brightest intrinsic object visible from Earth. And there it is in X-ray from the Chandra. And the reason it looks like this is because there is a relativistic jet pointing directly at us, the observer. Here's another different infrared spectrum, and this is the 2-mass. And this massive object, basically what's going on here, folks, let me bring up the large image. What's going on here is you've got this massive radio source, which is orbiting a Wolf-Rayet star, which is this massive star, and there's a huge disk of ionized gas and dust in between those two objects. This larger object has a relativistic jet, and it is aimed directly at Earth. It's one of the only known cosmic ray point sources in the galaxy, if not the only known cosmic ray point source, Cygnus X-3. The Wolf-Rayet star around which this object is orbiting is so massive that if it were in our solar system, it would be approximately the size of Mars's orbit. In other words, you'd be inside of it. And this massive radio source is making its orbit around this object in only 4.8 hours. So there it is on the Glimpse 360. That's also infrared light. Here it is on X-ray. And let's take one more look at it here. How about in infrared? No, not infrared. Let's take a look at blue light. All right, maybe not. Anyway, it's a void in the Milky Way galaxy, folks. And by the way, if you weren't aware, Göbekli Tepe is oriented at Cygnus X-3. And once again, you can see the Wolf-Rayet star here, but you can't see X-3 in red light. Anyway, there it is on the 2-mass infrared spectrum. Cygnus X-3, one of the more interesting objects, with a contested distance, by the way. We don't know if this thing is more like 2,000 light years away or more like 8,000 light years away. And let's check out the astronomy picture of the day from apod.nasa.gov. Here you're looking at two red giants, one up here and one down here, as well as Mars. And also some nebula, it's the Jellyfish Nebula. Along with Mars, and you can look at that yourself if you like at apod.nasa.gov. Last but not least, what about PEVATRONS? We've talked about PEVATRONS. This is a PEVATRON observatory, a high-altitude one located in China. As China is looking at PEVATRONS, PEVATRONS are gamma rays that are beyond the normal energy of gamma rays. So the most powerful gamma rays that we can create in CERN are 0.01 PEVATRONs. This is detecting photons at energies of 0.1 PEVATRONs. Although they're also detecting photons exceeding 1 PEVATRON, which is, I believe it's 1 quadrillion electron volts, folks. They detected one at 1.4 PEVATRONs, the highest energy photon ever observed at the China's Large High Altitude Air Shower Observatory, or LHAASO, LHAASO. So some more great science coming out of China there, detecting Cherenkov radiation and the highest energy photons ever detected at their high altitude observatory. And that's today's Cosmology segment. We hope you enjoyed it. I've been your host, Dan, aka smAsho, and we'll see you next time on our Cosmology segments.